In this problem, we're asked to find the line voltage and power factor at the source if the line voltage of the loads is 480 volts RMS. We have a balanced three-phase source. We have a line that has an impedance of 0.1 plus J.2, and we have two loads. The voltage, line voltage over those loads is 480 volts RMS. I'm going to designate this load is number 1, this load is number 2. And let's first calculate the complex power for each load. And what we'll do is we'll use Telegin's theorem, which says the source has to supply the complex power absorbed by the line plus the two loads. So we'll start off, calculate the complex power for the two loads, add that together, then we'll calculate the complex power absorbed by the line, add all loads together, and that'll give us the complex power for the source. So for load number 1, note that we're given 40 kilowatts. We're given the real power. We need to convert to kVA, so we're going to have to divide by the power factor. So it's 40 divided by 0.8. That'll give us the apparent power. The angle we get from the power factor is cosine inverse 0.8. And it's plus because of the lagging power factor. So we have 50 at an angle of 36.9, and that's 40 plus J30 kVA. Now for the second load, note that we're given the apparent power, we're given kVA, so we don't have to divide by the power factor, so we have 30 at an angle of cosine inverse 0.9, and this angle is going to be negative because of the lagging power factor, the leading power factor. So we have 30 at an angle of minus 25.84. So we have 27 minus J 13.1 kVA. Now we can add those two together, and I'm going to call that S sub T, and that's 67 plus J 16.9 kVA, and in polar form that's 69.1 at an angle of 14.16 degrees kVA. Now we can use that to calculate the magnitude of IL. We know the voltage, we know the complex power. So S sub T, the magnitude of it is square root of 3 VL IL. So if we solve for IL, we'd have S sub T divided by the square root of 3 times VL. So we have 69.1. That's in kVA, divided by the square root of 3. I'm going to convert this voltage to kV, so I'm going to make it 0.48 kV. That gives us 83.11 amps RMS. Now we can use that to calculate the complex power absorbed by the line, because the line current flows through those line impedances. So S for the line is 3 times 83.11 squared times 0.1 plus J.2, and that's 2.1 plus J 4.1 kVA. Now we can calculate the complex power supplied by the source. So S for the source then is S line plus ST. So we have 2.1 plus J 4.1 plus 67 plus J 16.9. So S for the source then is 69.1 plus J 21 kVA, and in polar form that's 72.22 at an angle of 16.9 degrees kVA. So there's the complex power for the source. Now the power factor of the source, we can get by taking the cosine of this angle. Is a cosine of 16.9, and that's going to be 0.9568, and it's lagging. And the reason I know it's lagging is the angle on S is positive. And so there's a positive angle that corresponds to an inductive load, and we know that gives us a lagging power factor. Now, then the magnitude of S for the source is equal to square root of 3 VL at the source times IL. So now VL at the source, we have the magnitude of S for the source divided by the square root of 3 times IL. So we have 72.22 kVA divided by the square root of 3 times 83.11, and that gives us 501.7 volts RMS.